Hello, I am the magnificent Mr. Daycock, and today I'm going to be teaching you how to differentiate functions such as sine, cosine, and exponential functions such as 2 to the power of x, or e to the power of x, or anything to the power of x. So to start us off, let's consider the question, if y equals sine of x, what is dy by dx? And this is effectively the question we're asking when we say, let's differentiate something. So to do that, what I'm going to do is I'm going to consider what differentiation means. And I'm going to remind myself that differentiation means finding the gradient of a curve. If we're looking at a graph, we're finding the gradient of it. And here is a graph of sine x. So what is the gradient at any given point? Well, at 0 here, at our point there, at our origin point, if we look, we can see that our gradient is basically 1. If I take one step to the right, I go up 1. Everything is exactly proportional, and our gradient is going to become 1, or is 1. Move along here and notice that this graph is in radians, and that's very, very important. If it weren't in radians, this gradient would be much, much shallower, if it was in degrees, because it would be much more stretched out along the x-axis, and therefore a much shallower gradient. Notice here at a half pi, we have a gradient of 0. Notice at pi, it's an exact reflection of at the origin, and so it's going to be -1. At 1.5 pi, or 3 pi over 2, we get to 0 again, and we end up with a gradient of 0. And at pi, we end up with +1 again, because everything repeats. And now if we continue in that way, we can see lots and lots of places where things are basically going to match up. Here we have a fairly shallow gradient, probably about a half. Just plug that in. Somewhere along here, much closer to this point, we have a very, very shallow gradient, a little bit negative, so we're going to end up with a point here like that. Whereas points close to here, they're fairly close to 1 still. And so we keep on going, we end up with something that's going to look like this. Something along those lines. And if I were to just fill this in, do part of my drawing skills, we're going to end up with this. Some of those points are off a bit. We're going to end up with something that looks like this, and some of you may recognize this graph. This is the graph of cosine. And so if I have y equals sine of x, my derivative, dy by dx, is going to be equal to cosine of x. Now, this is not a proof. We will be going through the proof in the next video, but what I want you to see is this makes sense. It really is the case that if I measure the gradient of the graph of y equals sine of x, I do get the graph of y equals cosine of x, or in this case, dy by dx is cosine of x, because we're looking at the gradient. And there's a nice little rule to remember to help us think about this. Well, that is basically the rule. Sine of x, I just like to draw this nice little diagram here, differentiates to cosine of x, which then differentiates to, and some of you will probably can see this, but it differentiates to minus sine of x. And if you want to be sure of that, just think about what's going on this cosine graph. Notice how the gradient is negative everywhere that sine is positive. Hence, to get this working, we need it to be negative. And of course, negative sine is going to differentiate to negative cosine. You can think of that just because it's the multiple of -1 of sine, and therefore we get a -1 multiple of the original thing. And then that differentiates finally back to sine. And we've got this nice little cyclic rule of sine, cosine, minus cosine. And equally, and this is a diagram I would highly recommend copying down, keeping with you if you ever think you might forget this. But equally, if we think about that, we can also think about ourselves in terms of integration. And integration is just going to be exactly the same thing, but going backwards. And that is how we would deal with integration if we were asked that question. But right now we're focusing on differentiation, so let's have a look at a few examples. So, find dy by dx when y is these various functions of sine or cosine. So if y equals 4 sine of x, this is very, very simple. It's just a multiple. It's just the same as 4 times by sine of x. And so we can just differentiate the sine of x. If we have a multiple of a function, we just differentiate it as though the multiple wasn't there. So the answer to this was just going to be dy by dx is equal to 4 cosine of x. Now for b, this is a very, very different situation. Notice how this is inside the function, and so this is going to affect it. And if we think about it, what's going on? If we're dealing with, if this here is the graph of sine of x, then what does sine of 4x look like? Well, everything's getting squashed. Everything's going to get squashed. It's going to look 4 times more squashed. And if it's 4 times more squashed, that means the gradient is 4 times larger. And so if we have this a coefficient inside the function, it actually comes out of the function. So we get dy by dx is equal to 4 cosine of, and our variable actually hasn't changed, so it's cosine still of the 4x. So our 4 gets repeated. Now for c, we've got 2 4's here. This one will not have any effect, but this one will. So what we're going to get? We're going to get dy by dx is equal to, we need to bring this 4 out, and then it's going to be multiplied by the whole thing differentiated, which is, as the first one, just 4 cosine of 4x. And that's going to be equal to 16 cosine of 4x. Notice how, if there's things on the outside don't affect anything, they just kind of sit there, but things inside are going to come out. Coefficients inside, multiples inside our function, are going to pop out and multiply by the whole thing. So similarly here, cosine, we're going to get dy by dx, we're going to get is equal to, that 5 is going to pop out and multiply by the whole thing. And then we're going to multiply by cosine differentiates to minus sine. So minus sine of 5x. And notice the 5 is still in the brackets. We're just getting that extra multiple of 5 in front. And so that's equal to minus 5 sine of 5x. And lastly, dy by dx, we're going to get that multiple, that third that's in here, is going to come out the front. So it's going to be equal to 1/3 multiplied by the whole thing, so negative 6. What's the derivative of cosine? Well, it's minus sine, so we're also multiplying by minus sine of 1/3 of x. So that negative 6 is sticking out in front. That negative sign has become from the cosine, and everything is being multiplied together, and that gives us, in the end, 1/3 of negative 6 is negative 2. But then we've got 2 negatives, so that's positive. So we're going to get 2 sine of 1/3 of x. And that is our final answer. Okay, so that is sine and cosine. Let's have a look at an exponential function. So here is a graph of y equals 2 to the power of x. Notice here, 1 to the power of 2 is 2. 2 to the power of 2 is 4. 2 to the power of negative, sorry, did I say 1 to the power of 2? 2 to the power of 1 is 2. 2 to the power of 0 is 1. 2 to the power of 1, 2. 2 to the power of 2. Here we're looking at 2 to the power of negative 1, which is a half. This is our graph of y equals 2 to the x. Now, what is the gradient at each point? What our question are asking is, what is dy by dx? Well, let's have a look. At 0, our point 0, 1, our gradient isn't quite 1. If I look here, it's going to end up slightly below 1. It's something slightly lower than 1. So I'm going to plug that in. At 1, well, if we actually look, it's pretty steep there, but it's not quite 2. It's more than 1. If I go take 1 step to the right, I go up more than 1, but it's not quite 2. It's about 1.5. So I'm going to plug that in. What about at 2? At 2, again, similarly, if I'm taking 1 step to the right, I'm getting a value of about 2.5, something along those lines. Let's put it about here, probably a bit more than 2.5. Let's go there. What about at -1? Well, if I take 1 step across, it's less than a half. It's a little bit less than a half, and so it's going to look like this. And what you should see as we go along is it's actually the exact same function, the exact same curve, except scaled down slightly. It's slightly less than the original thing. It's a multiple smaller. And this is always true. Of any exponential, y equals anything, any number to the power of x, then our rule is that dy by dx is equal to some multiple times by the same function. What is that multiple? And that's really, really key. Well, it's a function called the natural log of x. Or in this case, what we're going to be using is the natural log of whatever we're dealing with, which is n. And so, every exponential curve differentiates to itself multiplied by some multiple. So let's say I had y equals 3 to the x, then dy by dx would be equal to still 3 to the x, but with this appropriate multiple in front, which is the natural log of 3. And that's all there is to it. It's a very, very simple rule with one key point. There is exactly one graph, one exponential graph that differentiates. Because this differentiates to a multiple, there's exactly one where this c is equal to 1. And that is what we call our natural exponential. It's written as y equals e to the x. And if we have y equals e to the x, then dy by dx is equal to e to the x still. This is the key function that differentiates always to itself. And if you're asked for a function that always differentiates to itself, this is the function. And it's pretty much the only one within non-trivial one within some key conceptual bounds, which we're not going to get into right now. So let's look at those. Make sure you've got those rules memorized and understood. Let's look at these. So y equals 4e to the x. Well, as before, this is just 4 times by e to the x. E to the x differentiates to itself, so it's just 4e to the x. Here, we've got the 4 inside the function. It's part of the x itself. So we're going to bring that 4 out. Dy by dx is going to be equal to, thinking about that 4 multiplied by, and then everything acts as normal, and e to the x differentiates to itself, e to the 4x. And so we get 4e to the 4x. Similarly here, we've got that 4 in there, so dy by dx is going to be equal to 4 times by, and then 4e to the x differentiates to 4e to the x, but remember inside was actually 4x, so we end up with 4 times by 4e to the 4x, which gives us 16e to the 4x. That doesn't look like 16, let's make it clear. 16e to the 4x. Now, on to a slightly more complicated one. Dy by dx, this is 2 to the x. So we remember that it differentiates to itself, but multiplied by some multiple here, and that multiple is our natural log of 2. And so our answer is the natural log of 2 times by 2 to the x. Similarly here, well, we've got this 4 inside the function, and so it's going to be equal to 4 times by, and then differentiate the function. Well, 3 to the power of x differentiates to itself with some multiple, and that multiple is going to be the natural log of 3. And so our final answer is 4 lots of the natural log of 3 times by 3 to the 4x will be our derivative of 3 to the power of 4x. And that's all there is to it. Thank you very much for watching, and next time we'll be proving these rules. We'll be proving that our function e to the x differentiates to e to the x, and we'll be proving that sine and cosine differentiate to sine, cosine and negative sine respectively. Thank you very much for watching, and I'll see you in the next video.